Okay, so now we're going to talk about ordering sets. Now, so far in sets, part of our definition of a set is that it's unordered. The order doesn't matter. In the real world, when we actually physically put things into like a list or a vector or an array, there's always an implicit order. It's not always a straightforward order. If you think about things like a hash set, right, or a hash as a data structure, right, the order's kind of random, but they're in some kind of order. There's one, then the next, then the next, always. So because of that, it becomes important to look at ordered sets. It doesn't affect the correctness of your algorithm, but it will affect the speed that your algorithm runs at. So we're going to be looking at that for the next few examples from set theory. Okay, so with example 5, what we're looking at is lexicographic order, and that term's going to come up over and over again, and it's not nearly as scary as it seems. When we've seen lexicographic order many, many times, it's just a formal definition of dictionary order. So if we have, a T, TO, and AM, what order do they go in? Well, we know that we first order based upon the first character, so it's going to be, A T, then A M, and then T O, and then we order it based upon the second character, so we know that M's going to come before T, so it's going to be A M, A T, and then T O, right? That's dictionary order. We've been doing that our whole lives. This is no different. We just need to formally define that. And that's what lexicographic order is. Okay, so the formal definition is assuming that we have sets X and Y. And we'll define what X and Y are later, but just we have sets X and Y. And assuming we have tuples A and B, which are a member of X, Y, right? Remember that's that Cartesian product we talked about earlier. So A is a member of X, B is a member of Y. And assume we also have C and D, the tuple C and D, which is a member of X and Y. We say that AB is less than or equal to CD. We say that AB is before CD if 1, A is before C in the order of X, or A is equal to C and B is before D in the order of Y. So the order of Y doesn't even come into it until we've established the order of the first character X, of the first item in the tuple. Now, this doesn't look like dictionary order, but imagine that X and Y are the same set, and imagine that X and Y are the alphabet, right? Then clearly this looks exactly like what we just talked about. This is a more general definition where X and Y can be different sets. So let's move that off and let's make this a concrete example. Let's say that X is 1, 2, 7, and Y is the letter A and the letter B, right? So those are our two sets. What would be the lexicographic order of the entire set of all possible values? So that is, if we were to define the set for X by Y, what is the entire lexicographic order? Well, first we're going to have the tuple 1A, then we're going to have the tuple 1B, then the tuple 2A, then the tuple 2B, 7A, and finally 7B. So that is the lexicographic order of the entire set of the Cartesian product. of those two sets, which is what we would expect, but we need that formal definition for what we're going to do in the next example. Now, what about this case? What if we have x, y, and z that are members of x, y, and z? So what if we're dealing with a 3-tuple? Essentially, we've already ordered x and y, right? So we already have an ordering for every x and y. All we really need to do now is treat that as its own set and create another definition for ordering on z. I'm just going to say for this example, z equals smiley face, frowny face. Since we've already established what x and y are, if we have, say, the 3-tuple 1b frowny face, and we have 7a smiley face, we know that 1b comes before 7a, so just like before, it doesn't really matter what that last item is, what the last part of our Cartesian product is. Now, question. Does it matter if we put parentheses around the first tuple or if we put parentheses around the second tuple? That is, if we had x comma y comma z. Does it matter? No, because we can apply rules 1 and 2 just the same. It's just we apply them within that second set of parentheses instead. Now, the only way to prove that is to prove that x, y, z, x1, y1, z1 precedes x2, y2, and z2 if and only if x1, y1, z1 precedes, and you get the idea, x2, y2, z2. So that's the only way to prove that the parentheses doesn't matter. They do explain it in the book. I'm not that interested in it, right? It's intuitive. The parentheses don't matter. Once we've established lexicographic order for one set, or for one pair of sets, we can establish it for any number of tuples in our Cartesian product. And on a final note, remember, we're getting kind of complicated because we have all these different sets, which we will have in our homework exercises, but we do this all the time. It's just that x, y, and z are always our regular alphabetic set. That's the only difference. It's exactly the same. If you have any questions, ask in the forum below.